Now let us discuss how van der Waals gas equation can explain the nature of the compressibility factor. Now remember, the van der Waals gas equation is P plus A by V square, V minus B is equal to RT, which we are rewriting as P is equal to RT divided by V minus B minus A by V square. Now the compressibility factor was defined as Z equal to PV divided by RT. Now we will use the value of P obtained from van der Waals gas equation and insert it into the expression for compressibility factor to get which can be rewritten as Now remember that in order to explain the compressibility factor or the behavior of the compressibility factor in the low pressure regime, we can actually make an approximation. Since P tends to 0 in the low pressure regime, which means 1 over V bar is also tends to 0 and must be very much less than 1. So we can actually express this first term in terms of a Taylor expansion and write the compressibility factor as this is the Taylor series expansion for the first term, and then there is an additional term. Now we can ignore the higher order terms because in the limit P tends to 0, 1 over V bar also tends to 0. So we can just use the values only up to 1 over V bar. Thus we get Now remember how the compressibility curve looked like. It was Z versus P, and then this was the ideal behavior at Z equal to 1, and then for a definite gas the higher temperature curve looked like this, the lower temperature curve looked like this, and the intermediate temperature curve looked like this. So we are trying to explain the behavior at a very low pressure region or in this region. So in order to do that, we need to understand what is the slope of the curve. We can calculate it from the expression of the compressibility factor using van der Waals gas equation, which we just obtained. So what we arrived at for the expression of compressibility factor in the limit of very low pressure is Now remember, the compressibility factor expression on the plots were Z versus P or pressure, but in this equation we have molar volume. So what we can do instead is writing the molar volume in terms of P. Now strictly speaking, since we are using van der Waals gas equation, we should use the expression of P in terms of volume. However, since we are working or we are only trying to explain the behavior in the very low pressure regime, we can also use the ideal gas equation for the expression of the molar volume, which will give the expression for compressibility factor as 1 plus 1 over RT B minus A by RT into P. Now, in order to understand the slope of this curve at constant temperature in the limit when P tends to 0, we get an expression like 1 over RT into B minus A by RT. So the important quantity here which will dictate the nature of the slope, whether it is positive slope, negative slope or 0, is B minus A by RT. If B minus A by RT is greater than 0, the slope is positive, which will explain this region, which explains this type of curves. When B minus A by RT is less than 0, that will explain the negative slope of curves for some other temperature. And when B minus A by RT is 0, that will explain when the curve flattens out near 0 pressure. We just said that this temperature is known as boil temperature. So we can get an expression for the boil temperature, which we wrote as T suffix B as A by Beer. So the van der Waals gas equation yields an expression for the boil temperature in terms of the constants A and B, which means this boil temperature will be different for different gases, as A and B are constants which are different for different gases, which is experimentally observed also. Now let us try to draw the isotherms for the van der Waals gas equation. So I have drawn isotherms for 4 different temperatures. Now look at the first curve, which is at temperature T1. Here notice carefully that if you recall the curve which was obtained by Andrews, which were for real gas, that had a nature like this curve A, B, C, D, which we discussed. Now if we compare the Andrews curve with the curve that we obtained from the model, which is van der Waals gas equation, we get striking similarity in the region CD and AB, which explain the region where the substance is present as vapor, or the region where the substance is present in liquid. However, in the region when the substance is present as an equilibrium between liquid and vapor, the van der Waals gas equation yields a very different result from what is observed experimentally. We see that there is a rise region or high region, and there is a deep region. So this kind of peak and trough behavior is not observed experimentally. So if you carefully watch here, this region, here the pressure is actually higher than what it would be for the vapor pressure. So this region is termed as super saturated. Vapor phase. Similarly, the deep region or the trough region is called the supercooled liquid phase. These two phases are not real phases and they are metastable phases which we got by plotting the van der Waals gas equation. Remember, the reality is the experimental curve which was obtained by Andrews. Now we have a very interesting situation for the van der Waals curve. Let us redraw the curve at T1. Let us also draw a line which is parallel to the volume axis. As you can see that at this pressure, which we can term as P prime, there exist three different volumes which we can denote as P prime 1, P double prime 1, P triple prime 1, which all corresponds to the temperature T1. Now what does that mean? The substance can have three different volumes for this particular pressure. This is not surprising. This arises due to the cubic nature of the van der Waals gas equation, which we are going to explore in short. Before that, as we discussed the surface plot or the PVT plot for the ideal gas equation, we can also plot similar surface plot for van der Waals gas equation as shown in this figure. As you can see, at the very high temperature regime, this region, the surface more or less looks like an ideal gas surface. This is not surprising because ideal gas behavior is observed at high temperature limit. Similarly, in the very low pressure regime also, the surface looks like very much ideal like. So the van der Waals gas equation can satisfactorily explain the limiting cases, that is at high temperature and at very low pressure. The equation of state will reduce to the ideal gas equation of state, or the PVT surface will also look like that of an ideal gas. Now let us discuss more on the van der Waals curve or van der Waals isotherms. Now we can expand the van der Waals gas equation as this. And then we can multiply both sides by molar volume square and divide by pressure to get Now you see that the van der Waals equation of state is actually cubic in molar volume, and that was the reason why we got three different volumes for a particular pressure. Now interestingly, if you remember that at low temperature the curve looked like this, but at critical temperature when T is equal to Tc, the curve looks like this, which means all this crest and trough region, they coalesce, and all these three different volumes which we got for the same pressure, they all coalesce to a single volume which we call as critical volume. So at the critical point, we can write that the roots of the equation are degenerate, or all three roots of the equation are degenerate. If we call that root as Vc, which is the critical volume, we can write we can expand this expansion as now we have a very interesting situation. We said that at the critical point, I have an expression for a cubic equation like this, and also we arrived from the van der Waals gas equation, or the expansion of the van der Waals gas equation, that the nature of the equation is cubic. Now we can compare term by term for these two equations to get very interesting relations. If we compare the second term with the second term, or the coefficients of the second terms, we get 3 Vc is B plus RTC by Pc. 3 Vc square is A by Pc, and Vc cube is AB by Pc. The suffix C for P and T denote that we are considering the system at the critical point. So we can now figure out very easily what are the values of A, B and C from these equations. For example, if you take these two equations and divide the second equation by the first equation, you will get an equation in terms of Vc, and then the value of Vc will be given by just Vc equal to 3b. Similarly, you can get the values of Pc as A by 27 b square, and also the value of Tc as 8a by 27 br. So these are the values of the critical constants, which are Pc, Tc and Vc in terms of the van der Waals gas constants A and P. Now we could alternatively do another thing. We could write A and B and also the molar gas constant R in terms of the critical constant. If we just rearrange the expression for Vc, Pc and Tc, which we just obtained, we will get A is 3 Pc to Vc square, B is Vc by 3, and R is 8 Pc Vc by 3 Tc. Now let us do one thing. Let us incorporate these values of A, B and R into the original van der Waals gas equation, which is P is equal to, remember it was A by V square, and if we now incorporate the values of R, A and B from these expressions which we just derived, we get a very interesting relationship. This is the expression for R. RT divided by V minus B. Expression for B is Vc by 3, and then A by V square. Expression for A is 3 Pc Vc square divided by B bar square. Now we can rearrange this nicely to get T by Pc is equal to 8 into T by Tc divided by 3 into V by Vc minus 1 minus 3 into V by Vc squared. This is just rearranging this equation. Now we have a very beautiful situation. What is P by Pc? It is the ratio of the pressure to the critical pressure. Similarly, T by Tc is the ratio of the temperature to the critical temperature, and V by Vc is the ratio of molar volume to the critical molar volume. Now, if we denote these quantities by pi, tau, and phi respectively, we can write the van der Waals gas equation in a very compact form, which reads as pi is equal to 8 tau divided by 3 phi minus 1 minus 3 divided by phi square. So this is known as the reduced form of the van der Waals equation, because pi equal to P by Pc is known as the reduced pressure, V equal to V by Vc is known as the reduced volume, and similarly tau equal to T by Tc is known as the reduced temperature. Now, why we did it, or what is the point of arriving at this reduced expression? Of course, it is a compact expression, that is point number 1, but most importantly, it teaches us something else. Look at the original van der Waals gas equation, which is this. This equation contains constants like A and B, which are specific for a particular gas molecule. However, the reduced expression does not have any particular constant that represents one particular gas, which means just like in an ideal gas, there was no particular constant which is specific to a gas. We have reduced the van der Waals equation also in a similar form, which is independent of a constant which is very specific to a particular gas. So the loss of generality which was there in this original van der Waals gas equation has been regained in the van der Waals equation when it is written in the reduced form. Which means that if we do an experiment and plot say the compressibility factor as a function of not the pressure but the reduced pressure using this reduced equation of state, we should get similar curve for all the gases. To convince you this fact, here I show you the expression or the plots for compressibility factor as a function of reduced pressure, which we denoted as pi. Now note that this is plotted at various tau values or the reduced temperature. For a given tau, all the gases like nitrogen, methane, propane and ethane, they behave very similarly. They all fall on the same curve for any given temperature, which means they all now behave similarly. But now the trick is that they are not behaving ideally, because if they had behaved ideally, the value will be just the curve will look like just a flat line at z equal to 1, which is the ideal behavior. So what we did is that we cleverly replaced the constants A and B by the critical constants, which are Tc, Pc and Vc, and by taking the ratio of the pressure to the critical pressure and so on, we have defined few parameters which are reduced parameters. And if we plot the compressibility factor against the reduced pressure, it is no surprising that all the gas molecules should behave similar way, because there is no explicit constant in the equation that explains a particular or that actually corresponds to a particular gas molecule. So let me summarize what we discussed so far. We started with a discussion of ideal gas equation. We showed that ideal gas equation is only a hypothetical situation. However, real gases can obey the ideal gas situation only in limiting cases when the temperature is too high or the pressure is too low. Secondly, we discussed the deviation from the ideal behavior. There we discussed two main experiments, the variation of the compressibility factor with pressure as well as the isotherms for the real gases, which are known as Avogadro's curve and Andrews curve respectively. Then we discussed the development of a model, which is the van der Waals model, and we discussed in details the van der Waals gas equation. We discussed how van der Waals gas equation satisfactorily explains the existence of a critical point, but it cannot explain the liquid vapor equilibrium region. We also wrote the van der Waals gas equation in a very compact form and said the loss of generality, which was in the original form of the van der Waals equation where A and B constants were included, that generality, that lost generality is regained in its reduced form, which is more compact to use. In the next lecture, we'll start our discussion on classical thermodynamics. We'll first define few terms and then we'll move on and see how we can calculate different quantities which are measurable quantities for ideal gas as well as for a real gas, and for the real gas we'll use the model of van der Waals equation. Now before we finish, there are also many other models that are more accurate than the van der Waals model. However, we'll frequently use the van der Waals model here because of its simplicity of use. Thank you.